Hi guys, welcome to the series of tree data structures, and today we are going to learn one of the most important topics, that is representations of binary tree. So this is one of the must topic. Okay, so you have to understand the logic first, then you can do. So this is one of the must. So please do not skip this video and go through this, try to understand, and I'm expecting your supports. And representations of binary tree, one is we have array representations, another is linked representations. It's a linked representations is like a linked list, but we can say that linked representations and array representations is like just only array, where we can find like numbers of stack queue like that. So here we will go through this all, how we can represent this all binary tree in different. So first let's talk about the array sequential representations. Array is also called sequential representations of binary tree. When you talk about the array representations of binary tree, we can say that it's almost one traverse techniques, where we can traverse that all the elements in binary tree stored in array base. Okay, how we can insert that all data in as a array, as an array. So it's also we can say that array in the order which they are visited in a breadth first search. So this, remember that breadth search first. One is like this, we have two different types of search, we will talk about this. Okay, so let's is allow the efficient access of the elements of the tree. Here we can find different types of indices, and so that we can traverse easily. If the binary tree has n numbers of nodes, the array representations of tree can be stored in an array of size of n. So the numbers of node equals to the size of array, that also we can say. So for the constant time access to each nodes, because we will go through the one by one indexing by using the index. Here we can say the root nodes of the binary tree is stored at the first positions of the array. So and then its left right children are stored at the second and third positions respectively. So we can say, so you have to remember first as root nodes, and then other are like first and seconds. First left is second, and then right is third. In this we can show. So here we can find, if you are going to represent this tree, okay, this tree, here we have tree, one binary tree, like first root is a, b, c, and a has two children, that b and c, and b has again two children, that d and e, c has two children, f and g. So here total numbers of node is 7. So here are the numbers of size of array, also 7. When we talk about this, numbers of size equals to the numbers of the nodes, n nodes. And but in array, of course, we know that its indexes start from 0 to 6. And here if you add these two here, I'm talking about this, it's about complete. So it's about complete binary tree, or we can say that it's a binary tree with the different levels. So here is the left, but this size I have left. So in this also we can find this types of tree. I told you we have to go with the types of tree with the different. So here, while representing this up to 11 nodes, we can represent in this way. So here, like its indexes from the first, like a is 0, is the root is 0, and right, second is the left, third is the right children's, again root, right, left, in this way. So here if there is no value, so d has no children's, this means we can write -1, So generally in many book we can find here -1 written in if there is null, then you can write. In some cases we have seen that here null means 0. Either you can write null or you can write -1, so that we can understand that is null. So let's we can find the representations. How we can find or calculate? We have some properties that we can understand. So here when we talk about the array sequential representations in different positions according to the index as given the numbers of childs and children's of positions, we can calculate the numbers of nodes from the numbers of children, or we can find the index of the children's according to the parent. So here first is given it is possible to access the number of children, index of children. So index of children at the positions I by using the following formula. If parent parent indexing is given, then you can calculate the index of a child or children. So here this I is we are going to calculate as the index of the child, and if you are given this index of parent, so we can do this as formula. I will show you practically. It is also possible to determine the parents of node at the positioning I. Okay, so I using the formula this. If child node indexing are given, then you can calculate, you can find the index of its parent. Okay, parent is predecessors and child is the successors. That we will go through the practically, that will be the clear, I think. And for an example, we have total numbers of index here is 11. Total numbers of elements is 11, so we can go with the size of the array is 11. So here we can find, and when we will talk about the parent node, first let's take this as a parent node. Okay, so if the left child node is what? So as if you take the parent node index as 0, so first index, I'm going to talk about the first A indexing, that is 0 indexing that parent, this as a parent, and I'm going to find the left child of the first root. So left child is our B, so it must be indexing B. So let's how to calculate this. So we have here formula. By using this formula we can calculate. So as parent indexing is 0, so 2 into this is the index of the parent. Okay, so 0 plus 1 if you do, then its indexing is 1 of the parent. So this is the child index and this is the parent index. So in this way you can do. And next, this is the child. So next we can find the left child. How to find the left child if parent node is different? Suppose here I have taken as the parent node is 4. Okay, as the parent node is 4. So when you talk about the parent node is 4, that if you calculate, it provides 9. So 9 indexing, 9 is the index of child of the parent 4. So here we can find this is the child of parent 4 indexing 4. This is the 4 indexing, so we can find here. So this is 4 indexings it has. So 4 indexing, in 4 indexing we can find this is E has 9 indexing, that is yes. So this is the left side. In this way we can calculate. So as well as we can calculate the right indexing also. So let's talk about the right indexing. If right indexing also, if parent node is given 0. Okay, so here is given 0, and for the right indexing, to calculate the right indexing we have another formula, that is 2 into I plus 2, for left plus 1 and for right plus 2. So accordingly, if you go through, as I have taken as 0, so here like 2 into 0 plus 2 equals to 2. So our right indexing is 2 of that particular child. So here is the root parent is A and right child is indexing 2, that is C. So this side is the right side, so we can say this is the right side. So in this way we can calculate. Now let's calculate the parent indexing from the child indexing. Okay, so in the child indexing, so here is the parent indexing. We are going to calculate the parent indexing. For parent indexing, to calculate the parent indexing, we have different formula. So I equal to I minus 1 divided by 2. So first let's take one child index. So child index is 10. So I'm going to take here index. Child index is 10. So child index 10 is I. So immediate successors is the child and immediate predecessors is the parent. So we must find the parents. So when you talk about the I, so here is formula. When you calculate the formula, 10 minus 1 equals to divided by 2 equal to 4.5. Either here we can find here like point value, but we have to take as a floor value only. Floor value means we do not consider the point, only floor value, not ceiling value. Floor value means only 4. So 4 indexing is the parent indexing. So let's see, 4 indexing is the parent indexing. In 4 indexings we have E. So E has the child, that is 10. Okay, so you can see is clearly, suppose here is suppose here this is the child and this is the child, it has the parent is E, that is in index 4. So in this way you can calculate. And let's represent. So while talking about the advantages of the representations of the binary tree, we can say the easy to implement because it is easy, it is very simple and directly we can implement it. And more memory efficient because we don't need the memory space for different pointer to left pointer and right pointer, so that we can link it directly. You can insert it in sequential order and easy to access the children's. Of course we can access the children's through the indexing, and traverse are efficient because if you get the idea about that index, you can traverse in different traversing way, like pre-order traversing, in-order traversing, and post-order traversing. This all traversing, about this all different types of traversing we will talk in next video in detail. This is one of the most important also in tree, in the case of tree. So space utilizations, of course we can say that it's a memory, contiguous memory it is used. So in the case of space utilizations is perfect, efficient. But it has disadvantages. When you talk about the disadvantage, it is really very difficult to insert and delete from the array. Okay, very difficult because we have already fixed indexing. So if you delete any elements in the middle, you have to rearrange that all in again re-indexing. Okay, limitations of complete trees, of course, is like when you talk about the array in the tree, it has fixed size. So fixed size, if you said that you cannot increase that. If you increase, you have to reconstruct that tree, otherwise it's very difficult. Okay, so another is limit flexibility. It is not so flexible so that we can easily insert or delete. And next is fixed size. It has the fixed size. We have already talked about this fixed size because array has the fixed size. No complexity, no explicit pointers. No explicit pointers means also we can say implicit and explicit pointers to the like parent, child's parent or child nodes, so that we can navigate each other. Okay, so that is the disadvantages. So okay, And we are going to talk about the linked list representations, or it is also called linked representations. So while talking about the linked representations, it is the almost like a linked list, so where we can find the different pointers. So through that pointers we can link to the left child to the left pointer, and right child nodes to the right pointers with the value. So this is these are the different elements of a single node. Each node has these three elements. One is right node, left node, and then data, sorry, left pointers for the left node and right pointers for the right nodes. So we have to connect with this. So for an example, let's if you are given here such binary tree, and while representing in the linked list, we can find here the like this. Suppose here is one node, first node we are going to assign, suppose this assigned as a, okay, as a, and here we have to another, suppose this is the pointer of this, the first node as a root node, and we are going to assign another node, that is B, and B has also left right because we are going to insert with this pointer value. So B node has pointer 200, so this 200 pointer should be, it is the left side, so it must go to the left so that it connect to the left side. As well as if we'll go through the right side is also C, we have C, and this C has 300 pointers, so these pointers to the connect to the right side of the first root in this way. So you can connect to the next in the similarly this pointer address, the address of the elements of the node is must connect to the left and right. Like this way we can navigate to each of the nodes to the left, either left or right. Okay, so thank you for this much for this about this, and in next we are going to talk about some basic operations of the binary tree as well as traversals of the all in next video. So please keep it continue. Thank you.